Welcome back. Right, so what we're learning in this section is a whole new way of thinking about compound interest. And what we're learning here, I shouldn't say compound interest, let's say compound growth. Compound growth, and what we're learning here is, I just cannot stress the importance of this. It is really big. All right, so let's look at our compound interest formula, something that we know. Right? So we use compound interest to calculate out the amount of money earned when it is when interest is taken more than just at the end of the period, at the end of the year. Right? So our balance after T years is equal to our principal, that's the amount we're starting with, times 100%, 1, right? So you're going to keep it all, plus R divided by N, that's our interest rate as a decimal, divided by the number of times the interest is compounded yearly, and we're raising that to the total number of times compounded. So that would be the times per year times the number of years, right? So you're not getting all your interest at once, but you're getting a portion of it all the way through the year, and that interest is earning, so the next time the interest is calculated, you're earning interest on the interest. And we said that you would earn more money with when you have the your money, that's your principal being compounded more than once a year. Let's take a look at how much more. Right, so have a little problem here. As soon as it changes the page, which could be any day now. And there it is. All right, our problem. Vera has $1, a whole dollar, to invest for 1 year at 100% interest. Boy, you know, at that interest rate, I really want to invest more of my money. How much money will she have if the money is compounded yearly, semi-annually, quarterly, monthly, weekly, daily, 1,000 times a year, 10,000 times a year? Don't round these values. Questions. What trends do you notice? Is there a limit to how much money Vera can make in a year with her amazing, massive investment of $1? And these are the questions we're going to answer on the next slide. So I have this already all calculated out. I want you to kind of read through each one of these as I go through them. Save a little time, I already wrote them down. And actually, before I change the page, iron out somewhere on a little piece of paper, write down what you think Vera is going to make, in how much money she'll have. I shouldn't say how much she'll make. How much money will Vera have what's the most amount of money Vera could have? So that means that when it's compounded at 10,000 times a year, or maybe more, what's the most amount of money you think Vera's going to have in the account? All right, write that down somewhere. Make a guesstimate, all right? And let's see how close you are to the guesstimate. I think that'd be kind of interesting. And then tell me on Monday how close you were, all right? So if you need time to make up your mind about your guesstimate, and I am saying guesstimate because I don't want you to calculate it out, then you can pause the tape. But otherwise, I'm going to go right through and we're going to take a look. So once I turn the slide, if you're watching, you can't make a guesstimate anymore, all right? Because you would have seen the answer. All right, here we go. Come on. There we go. All right, so I have them numbered over here to match them over there. And I have the amount, the value with no rounding at all, and then to the nearest cent. All right, just because it's easier to look at to the nearest cent, but also I want us to see all of the decimals, all right? And you'll see why in a moment. Well, the first one I calculated out without a calculator. How about that? Because I had 1 plus 1, 2 to the first power. So that was $2. All right, so if it's only compounded yearly and she's getting 100% interest, of course she's going to double her money. That makes sense, right? But you see, if it's compounded twice a year, then she's going to make a little more money, right? Because we're going to calculate it out twice. And so whatever money she made the first time is going to get earned interest. That's going to get her a whole extra quarter. So here we'd be raising 3 halves, right, to the second power, and she'd get $2.25. And the third one, it's calculated, it's being compounded quarterly. So she's going to get 5/4 raised to the 4th power. That gave us 2.44140.625, which would round to the nearest cent. It would round to $2 and, oops, but not 24 cents, 44 cents. Didn't see I wrote that little boo-boo there when I was writing it down. There, $2.44. There we go. Right? If it's compounded monthly, right, she's going to get 13/12 raised to the 12th power. That was 2.61303529 rounded to the nearest cent. That was $2.61. If it's compounded weekly, right, it's going to be 53 divided by 52. Right, so it'd be 52 52s plus 1 52, and that would be 53 52s or 53 50-seconds. And that would give her 2.692596954, or rounded to the nearest cent, $2.69. If if it was compounded daily, she would get 366 to the 365th power, raised to the 365th power. And that would be equal to 2.714569482, which is $2.71. If it was compounded 1,000 times, right, that would be 1,001 divided by 1,000, raised to the 1,000th power, gives her 2.716923932, $2.72. So to the nearest cent, the last two are the same amount, but notice it's not the same decimal. Right? And if it was 10,000 times, so 10,001 divided by 10,000 would give her 2.718145927, or to the nearest cent, it's still $2.72. I'm actually going to do one more here, just to make it interesting, not that it's not already. And let's make it 100,000 times. All right, so that would be 1 times 1 plus 1 over 100,000 times. Right? And of course, it's 1, right? Because just in case you got confused, why is it 1 in every one of those? It's 100% interest, right? Right, so she's the 1 in the first one is she's keeping her $1. Right? She's keeping 100% of her $1, right? And she's gaining 100% interest. So the 1 is the 100% interest because 100% equals 1 as a decimal. There we go. All right, so 1 plus 1 over 100,000 to the, so that would be 100,000 times 1. Now, I don't really have to write the 1 in there, but that just helps you see that it was for 1 year. All right? And so I'm going to get a calculator, which should be behind me. And I'm going to raise, so this is 100,001 divided by 100,000. And I'm just adding the 1 and the 1 over 100,000. Just want to make sure that I have the right number of zeros there. All right? And I'm going to raise that to the 100,000th power. And again, I'm just checking to make sure I put in the right number of zeros. Yeah, I think so. So I get 2.718 2.718268237. I'm going to actually write that number down on the board over here because we're going to look at that number. Actually, I'll write it on this. We're going to look at that number in a moment, all right? So I'm going to write that down. 2.718268237. Notice that's still, if I round to the nearest cent, that's still $2.72. So she's not really making any more money here, is she, after this point? All right, so 3 times in a row I got $2.72. So technically, that's the most she's is going to make here is $2.72. But notice that the decimals are changing. Are now they're going to keep going up? Well, a little bit, but there's going to be a limit to this. All right, so some trends that you should notice. So first of all, it's not going up by very much after we get to 1,000 and 10,000 and 100,000. So there's not much difference. Between compounding it $1,000 or 10,000 or 100,000 times. But this is for $1. Notice that it would make a difference if it were $100,000, because we don't get anything more than that 2 at the end there. But what if I multiplied that by $100,000 instead of $1? So now those values would have a different meaning, wouldn't they? Because we would be getting that money, right? We wouldn't be rounding to the nearest cent anymore. Well, we'd be rounding to the nearest cent, but that cent is going to be someplace else. And all of a sudden, the difference between a 6 and an 8 becomes pretty significant if I multiply that, in this 6 and 8 here. So the difference between this and this doesn't mean a whole lot when it's $1. But if that were $100,000, right, that may be a little bit different, right? So there isn't a lot different. It starts to level out. It's still increasing, but it starts leveling out. And there is a limit, there was a limit to how much money Vera can make in a year with her whopping $1 investment. To the nearest cent, it was $2.72. That was the maximum she could make, no matter how many times we compound it. All right? So now, kind of remember those numbers. And I wrote down the last number because I'm going to put it back up on the board in a little bit so you can compare it to something. All right? So just kind of notice how those numbers are going and where they're headed to. So compound interest, of course, the amount of money you earn increases if n increases. But you may be surprised to discover that as n increases, the balance A approaches a limit. And we saw that on the last slide. And we have one of the most important numbers there is. It's right up there with pi in terms of its importance. And that is, don't spinning ball of death, there we go. Number E. The exponential function with base E is called the natural exponential function. Natural for living things. So y equals f of x equals e to the x, where e is an irrational constant. Irrational means it never terminates. Whose value is 2.7182818284590045. Let's compare that to what we had on that last slide, the very last one we did with 100,000. 2.718268,237. So if I had gone a little bit more, maybe made it 1,000,000 times, I would have eventually gotten closer and closer and closer and closer to this number. I'm going to bring the compound interest formula back on the next slide again so you can compare it to something. So notice that Vera's dollar that she invested, when we compounded it more and more and more and more times, it approached E, an extremely important number. Let's learn how important this is on the next slide. All right? Let's learn a little bit about E. Come on. Come on. Oh, and by the way, let me go back to the other slide, real quick. Oh, come on. There we go. want you to write this down, all right? You don't have to write all the decimals down, but you should have an idea of what E is and its value. So write down in your notes, before I go over how important E is, 2.71828. If you want to write the rest of them down, that'd be great, but you can just do that, all right? Just write that down so you have an idea of the value of E, all right? And you can also write in that it is the natural exponential function if I don't have that in your notes, all right? So if you need to pause the tape, just write that down. I'll wait here for you. Actually, you'll probably have it written down before my page turns. Now let's go over how important E is. Hardly contain my excitement over E. So you can see, look, all this time you have to write things down while I'm waiting for the page to turn. E is not just a number. It is a number, but it's not just a number. It's so much bigger than that. E is the base amount of growth shared by all continually growing processes. E lets you take a simple growth rate where all change happens at the end of the year and find the impact of compound continuous growth, where every nanosecond or faster you are growing just a little bit. That's how you are growing, right? Your hair grows, your nails grow, all those things grow. They don't all of a sudden pop, your hair is an inch longer. No, it grows a teeniest little bit that you can't even notice it continuously. Until after a while you say, hey, my hair's pretty long. E shows up wherever systems grow exponentially and continuously. Population, radioactive decay, interest calculated continuously, and more. So E is not an obscure, seemingly random number. E represents the idea that all continually growing systems are scaled versions of a common rate. You cannot understand population growth or how organisms change or biology without understanding the idea that all continually growing systems are just scaled versions of that same common rate. The discovery of the constant itself is credited to Jacob Bernoulli, who attempted to find the value of the following expression, which is in fact E. So the limit as n goes to infinity, in other words, as my n there gets larger and larger and larger and larger, that limit that we are approaching is the constant E. I think we've seen something that looks like that. Let's write that down. So A equals P times 1 plus R divided by N to the NT power. Doesn't it look like that? Little bit, right? Where R is 100%. N gets larger and larger and larger. Just keeps on growing, so it's going to infinity, which is what we did on the other slide, right? And this NT power is now just N times 1, because our R is 1. Oops. N times 1, right? And that's going to infinity. It's the compound interest formula as n gets larger and larger and larger and larger when we're earning 100%. That is E, and that is the rate of all continuously growing organisms. And we're going to be working now with continuous exponential growth and decay. I hope you feel the excitement, because I do. See you in class, and we're going to solve some problems with E. Bye for now.